All right, today we're going to unlock a really powerful idea, something that's used pretty much everywhere, from weather forecasts to medical diagnoses. It's called conditional probability. And really, it's all about asking a very simple but profound question. What if? It's how we update what we think is going to happen when we get new information. So let's dive right in. Just think about your commute home for a second. The chance of hitting traffic on any given day is, one thing. But what if you look out the window and see those dark clouds rolling in, and you hear the first few drops of rain? Suddenly, your prediction changes, right? You know that slick roads can mean more accidents and slower cars. That little word if it's raining, completely reframes the odds. And that's it. That little word if is the absolute heart of what we're exploring today. It's the core of conditional probability. It's the tool we pull out when knowing one thing fundamentally changes how we look at something else. And here it is. This is the master key that unlocks all of these kinds of puzzles. Now, I know, this formula might look a little intimidating at first, but the idea behind it is actually really simple. We're just asking, what's the probability of B happening given that A has already happened? And to figure that out, we take the probability of both A and B happening together, and we divide it by the probability of A happening at all. We're basically zooming in on the world where A is already a fact. And using this thing is a simple 3-step process. First, you just need to figure out what you already know, your givens. Second, you plug those numbers right into our master key formula. And third, you just do the math to get your answer. Let's actually put this to the test. Okay, for our first problem, we're going to do a really direct application of this rule. No tricks, no curveballs, just a straightforward run through so we can get comfortable with our new tool. Okay, so here's what we've got. We're told the probability of A is 1/2. The probability of B is 1/4, and the probability of both A and B happening, that's what this little upside-down U symbol, the intersection, means, is 1/10. So our job is to find the probability of B given A, and then flip it and find the probability of A given B. So we just plug the numbers straight in. For the probability of B given A, we take the intersection, that's 1/10, and we divide it by the probability of A, which is 1/2. That gives us 1/5. Easy enough. And for the probability of A given B, we take that same intersection, 1/10, and this time divide by the probability of B, which is 1/4. And that gives us 2/5. See? It just shows how the formula works in its simplest form. All right, let's level up a bit. What happens when the problem doesn't just hand you everything you need? For this next one, we're going to have to find a missing piece of the puzzle before we can even think about using our master key. Now, what's really interesting here is what's missing. We have the probability of A, we have the probability of B, and we have the probability of A or B happening. That's what the union, the U shape, means. But look, we don't have the probability of A and B, the intersection. And without that key piece, our master key is totally useless. So, how do we find it? Well, we're going to need a new tool for our toolkit. Meet the union rule. It says the probability of A or B happening is just the probability of A plus the probability of B minus the probability of them both happening. Now, why do we subtract the intersection? Simple. It's to avoid double counting the part where they overlap. But for us, this is perfect because we can just rearrange this formula to find the very piece we're missing. Let's do that right now. We just shuffled the formula around to solve for the intersection. It's simply P of A plus P of B minus P of A union B. We plug in our numbers, that's 1/2 plus 1/3 minus 2/3, which gives us 1/6. And that's it. That's our missing piece. Now we are in business. With our shiny new intersection of 1/6, we can finally go back to our master key. The probability of B given A is our new intersection, 1/6, divided by the probability of A, 1/2, which equals 1/3. And the probability of A given B is 1/6 divided by 1/30, which equals 1/2. Perfect. We found the missing piece and we solved the puzzle. Okay, let's bring in another powerful concept. Sometimes you don't actually know the overall probability of something happening directly, but you might know how it behaves under different conditions. Like, maybe you don't know the overall probability of a flight delay, but you do know the chance of a delay if it's sunny and the chance of a delay if it's snowing. this is where we need another key for our toolkit. This is the law of total probability. And again, it might look a little complicated, but it's incredibly intuitive when you think about it. It just says the total probability of some event B is the sum of its probabilities across all the different possible scenarios. So going back to our flight example, to find the total probability of a delay, we take the chance of it being sunny times the chance of a delay if it's sunny, plus the chance of it snowing times the chance of a delay if it's snowing. We're just adding up all the ways it could happen. So let's apply it. We're given that the probability of A is 1/3. Now that automatically means the probability of A not happening, that's what the little bar over the A means, is 1 minus that, which is 2/3. The problem also gives us the conditional probabilities for each case, so we just plug them in. 1/3 times 1/4 plus 2/3 times 1/2. Do the math, and it simplifies down to 5/12. That is the total probability of event B. Okay, it's time for the final challenge. You can think of this as the boss level. We're going to combine everything we've learned so far and introduce one final idea: complements, or the probability of something not happening. So here's the setup. For part A, we're going right back to our basic conditional probability calculation. It's a nice little warm-up. But for part B, things get interesting. We need to find the probability of both A not happening and B not happening, and then use that to find the probability of B not happening, given that A hasn't happened. This is where we bring it all home. Let's knock out the easy part first, shall we? Given our initial numbers, part A is just a simple plug and play with our master key formula. P of B given A is 4/5, and P of A given B is 8/15. Done. Okay, now for the fun part. So here's the key insight for this one. The probability of not A and not B is exactly the same as 1 minus the probability of A or B. So we use our union rule to find PA union B, which, after plugging in the numbers, comes out to 17/20. So 1 minus that gives us 3/20 for the intersection of the complements. Then we just plug that into our conditional formula. 3/20 divided by the probability of not A, which is 1/2, gives us our final answer, 3/10. We did it! And just like that, you've pretty much mastered the fundamentals. You know, you didn't just solve a few math problems here. You've actually built a powerful toolkit for thinking about uncertainty and for making better decisions as the world around you changes. So let's do a quick recap of the 3 essential tools you have now. You have the master key of conditional probability for asking, what if? You've got the union rule for finding those missing pieces, and you have the law of total probability for figuring out an event's overall chance by looking at all the possible scenarios. You see, this is so much more than just numbers and letters on a screen. It's a whole new way of thinking. This is used in weather forecasting, in medical diagnoses, in machine learning, so much more. So the real question I want to leave you with is this. Now that you understand how to ask what if using math, what puzzles in your own world are you going to start to unlock? I'm genuinely excited to see what you come up with.